You know, every time you open up LinkedIn and you see that little second or third degree label right next to someone's name, you are actually looking at the output of one of the most fascinating graph problems in all of distributed systems. Seriously, it's a real puzzle. Welcome to This Explainer. Today, we're going to completely deconstruct exactly how to design this graph architecture. And we're going to do it at a level that would actually pass a staff engineer interview at companies like Google, Meta, or, well, LinkedIn itself. We are treating this as an absolute masterclass in whiteboarding complex systems. So let's get right into it. All right, here's our roadmap for This Explainer. We'll be covering 1. The core constraint, 2. Storage foundations, 3. The read path, 4. Algorithmic optimization, 5. The write path, and finally, 6. Those crucial staff-level edge cases. Starting off with Section 1, the core constraint, we are going to prove exactly why live traversals are mathematically impossible here. Okay, before we even think about drawing a single box or arrow for our architecture, we absolutely have to establish the foundational requirements of our system. To design this right, we need to ground ourselves in the hard numbers. The API we're building basically takes a source user ID and a destination user ID, and it has to return their degree of connection. First, second, third, or maybe they just aren't connected at all. And the scale we're talking about? Roughly 1 billion users and about 500 million edges or connections. Now listen to this read volume, 500,000 queries per second. That represents literally every single profile page load, every search result, every feed item. And we have to serve all those reads with a super strict latency target of under 50 milliseconds for 99% of requests. Which brings us to arguably the single most important insight in this entire design. Let's just mentally walk through a naive live breadth first search, or BFS traversal. Imagine you're right there at the center. At hop 1, you visit your immediate connections. Let's say that's a pretty reasonable 500 neighbors. Totally fine. But at hop 2, you have to visit the neighbors of all 500 of those people. Boom. That suddenly explodes to roughly 150,000 nodes. And at hop 3, things get completely out of hand. You're suddenly looking at loading the adjacency lists for 20 to 30 million nodes. 30 million nodes. Just pause and think about that number for a second. If you actually tried to run a live breadth first search out to 3 degrees of separation on every single API request, you would instantly crash your system. No question. Hitting 30 million nodes makes a live BFS mathematically impossible when you're dealing with 500,000 queries per second. We clearly need a completely different approach. That brings us to Section 2, Storage Foundations, why LinkedIn actually chose predictable key value stores over traditional graph databases. So now that we know we absolutely cannot compute this on the fly every time, how do we actually store the graph data? You might be wondering, hey, why not just use a dedicated graph database like Amazon Neptune? Well, graph databases are incredibly amazing for exploratory traversals, where you don't really know the depth of the path you're looking for. But our query pattern here, it's rigidly fixed. We are always just asking the exact same thing. Give me the neighbors of node X up to degree 3. So the crucial point here is that LinkedIn's fixed query pattern perfectly suits a custom key value store, specifically HBase. They basically store the graph as a giant adjacency list. User A's row simply contains the list of all the users A is directly connected to. It's incredibly predictable and it's highly optimized for our exact specific need. So in HBase, we maintain what's called a materialized degree store. Just think of it like a massive lookup table where a user's row contains distinct sets of their first, second, and third degree connections. Now, what's really brilliant about this approach is the specific data structure they use for those sets. Roaring bitmaps. A roaring bitmap is this highly compressed bit set that's fully optimized for integers. Remember those 150,000 second degree connections we just talked about? Well, roaring bitmaps can compress those 150,000 user IDs down to just 50 kilobytes. It's wild. And the best part? They still allow for instant O1 membership tests. This one piece of engineering right here is a real game changer. It's what makes storing millions of connections tractable at this kind of scale. Moving on to Section 3, the read path. We're looking at the 3-tier architecture. Because live computation is just way too expensive, our read path has to be this beautifully layered abstraction. It's designed to handle 99% of our traffic gracefully before doing any actual heavy lifting. Picture it like a 3-tier funnel. When a request comes in, the very first stop is Tier 1, the Redis cache. The The key is just the source ID and the destination ID. If we get a hit there, we return it in basically 1 millisecond, and that handles over 95% of all traffic. Now, if there's a cache miss, we smoothly fall through to Tier 2, the HBase degree store that we just broke down. We check those compressed, roaring bitmap sets, which takes about 5 to 20 milliseconds. Finally, if the destination ID isn't an HBase at all, maybe it's a brand new connection, we drop down to Tier 3, the live BFS engine. This is our absolute last resort, and it is heavily protected by a hard 200 millisecond timeout. Which leads us perfectly into Section 4, Algorithmic Optimization, the mathematical proof for bidirectional BFS. Okay, so what actually happens when we do inevitably hit that Tier 3 fallback? How do we stop our live BFS from exploding into those 30 million nodes we warned about earlier? Well, comparing the two approaches mathematically literally proves the difference between total failure and success here. A naive unidirectional BFS expands only from the source. It loads 150,000 nodes just to check depth 2. But the actual production solution is a bidirectional BFS. You expand from both the source and the destination at the exact same time, basically looking for a meeting point right in the middle. By doing it this way, you only visit roughly 400 nodes from each side before they intersect. You shrink the workload from 150,000 nodes down to about 800 nodes total. It is a massive quadratic speedup. And we actually optimize that bidirectional BFS even further. First off, we always expand the smaller frontier first. This is absolutely crucial. If the forward search has 200 nodes and the backward search has 500, we expand the forward one. It deliberately keeps the overall workload balanced. Second, we enforce early termination at depth 3. If they haven't met by then, we just stop entirely and return null. Finally, whenever this live BFS does successfully find a path, it asynchronously writes that result right back to HBase and Redis. This ensures our faster tiers can easily handle that exact same request the next time around. Next up, Section 5, the write path. Let's look at managing asynchronous writes and the invalidation problem. So, we've totally mastered reading the data, but what happens when user A actually clicks connect with user B? Let's trace that write pipeline and see how this builds our asynchronous architecture. The very moment a new edge is created, it's written synchronously directly to the primary GraphDB. That's our absolute source of truth. Immediately after that, an edge_added event gets published to a Kafka topic. From there, two totally separate asynchronous consumers pick it up. You've got the cache invalidator, which clears out stale data, and the degree updater, which actively patches the new connection into our HBase sets. But wait, there is a massive hidden trap here, the cascading invalidation problem. Think about it. If user A connects to user B, it doesn't just affect them. Literally millions of their connections just got brand new second and third degree links. If you tried to aggressively delete every single affected cache key across millions of users, your system would absolutely be crushed by what's called a thundering herd of delete operations. The elegant fix for this? Version stamps. We simply store a version epoch number on each user's record. When they make a new connection, we just increment their specific version number. Any cached entries floating around with older version numbers are now officially considered stale, and they get lazy invalidated the next time someone tries to read them. It's brilliant. Problem solved, and no thundering herd. Finally, Section 6, Staff-Level Edge Cases. Let's talk system resilience and handling the extremes. This right here is where a good design becomes a truly great design. We have to bulletproof our system against failures and just really extreme data shapes. Let's talk system resilience. What if Redis just goes down? Well, the system degrades gracefully by falling back to HBase. Sure, it's slightly slower, but it's entirely acceptable for the user. What if the Kafka queue is lagging? We rely on eventual consistency. A 1-hour staleness window for a new social connection is perfectly fine. But the ultimate safety net? That's the nightly distributed Spark job. Every single night, a massive offline batch job recomputes the first, second, and third degree sets for all 1 billion users entirely from scratch. It acts as this incredible self-healing mechanism that just overwrites any missed updates from the day. And this brilliantly illustrates something else, the extremes. What actually happens when your live BFS traversal hits an account like, say, Satya Nadella's, which has millions of connections? That is a fan-out explosion that will immediately melt your database. We call this the celebrity node problem. To protect the system, any user with over 1 million connections is just flagged as a meganode. During a live BFS, these meganodes are explicitly skipped as intermediate hops because honestly, they just create noise and offer no meaningful signal for a personal connection. Instead, their massive degree sets are purely pre-computed offline and cached permanently so they never break our live day-to-day operations. And for our last edge case, there's the reality of distributed data. User A is sitting over on shard 3, but user B is on shard 7. Doing sequential lookups across these shards during a BFS, that would add massive latency. To solve this, we use parallel cross-shard hops. At each depth level, we batch all the neighbor lookups together, we dispatch those queries in parallel across all the relevant shards simultaneously, and then we just merge the results before moving on to the next step. This whole process keeps our latency incredibly low, regardless of how fragmented the data is under the hood.
So we have systematically dismantled exponential complexity today, using predictable KV stores, roaring bitmaps, bidirectional algorithms, and asynchronous event streams. We've successfully built a highly resilient architecture that scales all the way up to the 3rd degree of connection. But I'm going to leave you with a staff-level question to ponder. Considering the massive exponential node explosion we explored today, how would you adapt this exact architecture to calculate the 4th degree? Think about it. Thanks so much for joining this explainer, and keep designing.